In this section, we're going to continue to talk about acids and bases, and I'm going to get into some of the ideas on how chemists understand which things are going to react and how we know things are strong or weak acids or bases. And one of the first things I have is a table here from your book that lists all of the strong acids and the strong bases. And what this means when we're talking about a strong acid or base is that these dissociate completely. So they fall apart completely in solution. So this figure here that you can see is something like we have methanol. And here you have that alcohol functional group and an organic compound. And when you put this into a solution and you hook this up to an electrode, there's not much of a current that goes through this solution. And what that tells us is that OH group, the hydrogen doesn't fall off readily. And what is required to have that electricity flow through here is that we have some charged compounds. We have to have a positively charged compound or a hydrogen for that electron to kind of flow through. And we can see that through this light bulb isn't lit up. That means it's not charged very well. Here we have sodium chloride, and these ions fall apart. So we have spots where the electrons can float through these positive charges and get from one electrode to the other, and that allows us to connect this circuit, and we can see that light bulb lit up. So that means that this conducts electricity because it has charged states. That's going to be for all of these strong acids and bases. These are going to fall apart completely. The hydrogens are going to fall off of these compounds, and we're going to have negative ions left behind. In some cases, right, polyatomic compounds. And on these bases, we're going to have the OH groups falling off, and we're going to have those negatively charged groups. So this tells us something about the ions and how well they are able to dissociate. So these dissociate completely. So they'll give us a really good current through that solution. Here's another example of more of a weak electrolyte. So you can see here we have COOH. You might recognize this as a carboxylic acid functional group. Now, every once in a while, or more often at least than this alcohol functional group, we'll have these ions forming. We'll have CH3COO- and an H3O+, or right, that's kind of discussed in your book, and we've talked about this, where that H+ ion really technically will bind to a water molecule instead of just floating around freely. So we can see that positive charge. We have electrons that can kind of flow through that positive charge from one electrode to the other and complete this circuit. Now, it's certainly not as bright as this compound, which would be like a strong acid or a base. It's pretty weak and it's pretty light there, but we can have some of the time that will happen. So I'm going to show you a mechanism that we can look at that will tell us a little bit using more of a quantitative value, looking at those ideas from the last lecture where we're talking about pKas and the different equilibrium constant. It's really about that. It's how well at equilibrium these are falling apart. So the more of these that have fallen apart at equilibrium, the more of the electrode is going to be good, and the more of these fall apart in our solution. And the difference, if the equilibrium state is more at the reactants where they're together in a compound, then we're going to have a more weak electrolyte. So we'll look at those values and we'll look at those ideas in this section as well. I do also want to point something out here for you. In the book, you'll notice maybe this figure, and perhaps you noticed that that we have, I told you about aeroformalism. Now, I'm not really super excited about how they've depicted this in the book, where the arrows are going from the proton and they're moving protons. Normally, we don't do that in organic chemistry. So these are typically, we're going from the electrons, we're showing where electrons are moving. So I would have preferred if that figure had been shown like this instead, and these electrons bumping off to the oxygen. This is a more accurate depiction of what is happening. And then with this other compound, we would have the oxygen would be attracting that proton with those electrons, and then the electrons between the hydrogen and the chlorine would fall apart. So this is proper aeroformalism. They are just showing kind of the movement of the proton instead. And I just wanted to point that out, that they weren't using arrow formalism in that figure. But I think that's how people sometimes get confused because, you know, depending on what you're trying to show. But this is how you would draw this out using proper arrow formalism. Another possible reason that the kind of this was the way it was, how they drew that out, is the difference between the Arrhenius acids and bases and the Bronsted-Lowry acids and bases. And remember, the Arrhenius acids and bases are going to be when we make H plus or OH minus in solution. So here you can see that we have made OH minus, so that would be an Arrhenius base. However, we didn't necessarily make an H plus. We actually bonded that proton onto another molecule right away. So this would be a Bronsted-Lowry acid because it's not going to necessarily make H plus in solution. But it would be a Bronsted-Lowry base or an Arrhenius base. So there's some distinctions. I'm not super worried about you being able to distinguish those, but it's kind of the same idea, but there's the subtle distinguishing characteristic of those different kinds of things. So Bronsted-Lowry definition, we are donating a proton. That is the acid. And then for the base, we're going to be donating a lone pair or pi bond electrons. So that's the difference. And you can see down below here, we're donating the lone pair of electrons. So this could act as a Bronsted-Lowry base. But we're also, on the right side, we're not necessarily making the OH. So no OH. So this wouldn't necessarily be a Bronsted-Lowry base. We are donating a proton, and you can see here. So it could be an Arrhenius acid or a Bronsted-Lowry acid because we're donating the proton. So in either case, so these are the fine distinctions between these terms. So I mentioned I wanted to talk to you more about this idea of how we get numbers, numerical values, so we can be quantitative, so we can have some values that help us determine if something's going to be a stronger or weaker acid. I showed you on that other table where we looked at really strong acids and bases. So you can see here, HCl, this is an inorganic acid, and it's a very strong acid. And all of those on that list on that previous slide, all of those compounds of the acids and bases are going to fall apart and be really strong. So this is just one example that's put in here to show you that this pKa value is a -7. Remember, our pKa, our Ka values, are equal to the products, the concentrations of the products, over the concentration of the reactants. And that means that our products are going to be the chemical reaction is moving forward. So and remember, the pKa is, if this is going to be, let's say, 1 times 10 to the 7th, the pKa is the negative log of the Ka. And that means that if the pKa, this is going to be a -7, this is a really big number. 1 times 10 to the 7th is really large. So that means that this falls apart very easily and readily, and it's a very strong acid. And you can see the continuation of these pKa numbers until we get down to a methyl group and just the hydrogen on the methyl. How good of an acid is that hydrogen? And we can do that same idea where we look at this pKa value. And if I know that this is the pKa, I can say that the Ka is equal to 1 times 10 to the -50th. So that's how we convert between those two. That number is super small, right? To the -50th power, it's 0.0000050 zeros long, right? 1. So not much of this falls apart in solution. So this is a very, very weak acid. Very, very. And this chart gives us a general idea of what kind of different functional groups are going to be stronger acids versus weaker acids. So if we look at this compound, this list, we have a carboxylic acid. Acid's even in the name. So as an organic compound, this acid has a relatively good pKa for being an acid. So this is hence the name. There are a lot of acids that would be involved in organic compounds and biomolecules that are going to be acting as weak acids, but they're strong enough to do something in solution and to have chemical properties. And so that one is going to be the strongest of some of the organic compounds that we'll be looking at. If we're just looking at water, we can see that the pKa, just as a reference point, carboxylic acid, stronger acid than water. And this is kind of a good reference point. 15.7 is the pKa for water. Now, if we're looking at this group is an alcohol group. And we can see that the pKa here is 16. So it's this is weaker than water. So if we put alcohol in water, what that would mean is that probably not much of that alcohol would interact with water as an acid. So it would keep that OH group would stay on there likely. So when we're looking at these pKa values, we can think about them. If we have two of these compounds in solution with each other, this pKa value will determine which one's going to be the acid and the base. So which ones might give a proton to the other compound or not. And so that's what's going to help us with these pKa values. So here we have an alkyne. And you can see that that's about 25. We just have a hydrogen, molecular hydrogen. (35), we're getting weaker and weaker. An amine, even weaker at 38. An alkene and an alkane. So you'll notice as we get from alkane to alkene to alkyne, then that pKa value gets lower and lower, and this becomes stronger as we go from a single bond to a double bond to a triple bond. And we'll talk about that in a little bit in terms of why that is. But this is just a general good chart to kind of be able to kind of differentiate between the different acids and their strength. And that's based off of this idea of the pKa value that we spoke about in the last lecture set. Okay, so I want you to take a moment here and I want you to rank these conjugate bases and of each of the groups of acids in increasing basicity. So let's look at this idea here first. I'm going to actually show you B, and I want you to do A for me in our Blackboard space. So if we're looking at, first we have to look at the pKa of all of these. So with a alkene, this is going to be 44. This is going to be 25. And then we have a 50. So this is for acids, we know that the 44 is the middle. So we have mid, strong, weak for acids. And there's an inverse correlation between the strength of the acid and the base. So then we can look at the base. So we always look at the pKa, and then we identify the strong versus the weak and for the acid, and then we can say, okay, then it's the opposite for the base, the conjugate base. So now the strongest acid is going to be the weakest base, and the weakest acid is going to be the strongest base, and the middle one's still going to be the middle. And this kind of gives us an idea. That's what this chart is kind of giving us, this on the right side for the conjugate base. So this should kind of make sense because this tells us that that compound is relatively stable. As an ion, chloride ion is stable, so it's not going to necessarily want to kind of revert back to the acid form. So this tells us something about the stability of our products, this increasing basicity. And this compound on the bottom is the least stable. It would rather be a molecule without a charge on it. So that's for B. Please look at this and kind of do that also for A and post your answers in our Blackboard space. I would also like you to identify these different functional groups and also recognize what the pKa might be for those. And again, I'd like you to use that table that I've been showing you. I will show you one thing I think that's a little bit tricky, how this is labeled. I'm going to just show you an example for C because I think that's the trickiest one. For C, this is the whole functional group. So you can't just take this as an alcohol because that whole thing is all connected to each other. So this is actually the carboxylic acid. So the pKa for carboxylic acid is listed in the table. It should be 4.8. So it's important to be able to recognize these functional groups so you can distinguish this is 4.8 and not 15, or sorry, not 16, right? This is not an alcohol. Its alcohol group is on there, but it is more properly termed as a carboxylic acid because it's attached to this carbon that's attached to a carbonyl group as well. So this is a carboxylic acid, and that's that trick there. So here also recognize that this one is highlighted on a carbon that has a double bond. So you have to recognize the whole functional group, not just part of it. So if you could identify those groups in this table, that would be great. And then post those answers for A, B, and D in our Blackboard space. So you might ask then, why do we care what the pKa values are? Well, it can help us determine what chemical reactions might be happening and which direction they would go into. So theoretically, both of these two compounds have protons, and theoretically we have pi orbital electrons, and we have lone pairs, so they could either act as acids or bases. But if we go back and look at the different conjugate or the different compounds, we know that we have the pKa value is a 25. And this is a base because it's negatively charged. So we can start to use this idea of if this is going to go forward or backwards to kind of give us this idea of what chemical reactions are going to happen. So let's use this because we have a negative charge. We talked about that in the last section, that if it has a negative charge, it will more likely be donating electrons. And this is the chemical reaction that we're going to look at here. So if we have the acid and the acid over here in the alkyne, and we have the base, we're going to create our conjugate base and our conjugate acid. And we can look at the conjugate acid, the pKa here is a 38, and we can compare that 38 to the 25, and we actually know that the 25 is a stronger acid. And that means that actually when we look at this, that means the equilibrium should lie to the right, should lie to the products. Because if we're going to go head to head, we typically look at pKa values just for the acids, for the acid, the starting point acid, and the conjugate acid, and we can determine which is stronger. And that's going to tell us if the reaction is going to move forward or if it's going to just stay where it is and not move forward. And this is how we can determine this using pKa values. So here I'd like to show you another practice problem, and we're going to use the pKa value. So I'm actually going to do the second one here to show you the compound here. I'm going to do this one. So I'm going to redraw it out so I have my protons available for chemical reaction, and I'm going to have all my lone pairs of electrons shown, and we know that this is a negatively charged. So it's probably going to be our base, right? Because we know that's something that has a negative electron. It's a hydroxide, which you can start to also recognize that that would be a base. This is going to be our base, and we're going to donate electrons to a proton. So I'm going to draw that out, and then I'm going to break that bond between the adjacent hydrogen and carbon between them. So here we're going to create that new compound, and I'll draw that the equilibrium arrows out. And we're also going to then have H is going to be attached to the oxygen, and we're going to have that water compound now. And then we're also going to have that carbon with a lone pair of electrons, and that's going to have a negative charge. We can do formal charge. Normally carbon has 4 valence electrons, and now it has the 1, 2, 3, 4, 5. So it should have that extra electron. It'll be that negative charge. So this would be our reaction. Now we want to look at, determine where does the equilibrium arrow go towards. So we're going to have our acid is going to be this methyl group. So the pKa is going to be 50. And here the acid is going to be water. And the pKa, the conjugate acid, is 15.7. So this is stronger, which means that this chemical reaction, we're actually going to have a stronger chemical reaction going to the left. The stronger acid is going to prevail. And let me get, so we're going to, a little bit can go to the right, but a majority of this is going to go left. This tells me that nothing's going to really happen. If I have a strong base in solution and I have an alkane, nothing's going to happen. The chemical reaction is not going to react with this alkane. So this tells me something about the chemical reaction that's going to happen. And this pKa table can be really useful for understanding that. So please do this with the alkene and this hydride compound, and then I'd like you to post your answer if this is going to go towards the reactants or the products based off of your determination using pKa values. As I mentioned, we can use this idea of pKa to determine if something is going to happen, if the chemical reaction is going to happen. So we saw in that last example that I showed you, it wasn't going to happen because the pKa of the conjugate acid was lower than the pKa of the starting acid. Let's look at another example here. So if we're looking at something, we have the NN-dimethyl acetamide, and that's shown here. And then we want to look at if the equilibrium favors some of the products here. So let's look at these different compounds. So if we have sodium as the counter ion, NH2 with a minus charge is the base. So we have this base compound. We're going to add an acid, and we're looking at the pKa. This final product is going to be a 38. So 38 compared to 30, this is a stronger acid. So that first reaction, this reaction will move forward because this acid is weaker than the starting acid that we're reacting with. For B, if we have hydroxide as the base from sodium hydroxide, and we're going to add this proton from this compound, and the pKa is 30 versus the 15.7 is the final pKa, this chemistry isn't going to work. Nothing's going to happen because the product is a stronger acid. So it's going to fight its way back to the other direction and maintain the reactants. So this one would not proceed. So if we're looking again, if we're looking at these differences here, it depends on the starting acid point. Just to reiterate that, you can see here, if we're looking at the conjugate acid, for this product is going to be 38, and the starting acid is 30. So this one is going to move forward. However, for the second reaction, the conjugate acid is 15.7, the starting acid is a 30, and this one's not going to move forward because this stronger acid is going to be a product which would fight its way back to making the reactant. So this one won't proceed. Now I'd like to look at why some of these trends exist and what the rationale is, or the reasoning for why some of these things might happen in terms of the pKa values. So if we look at the periodic table, we can see a similar setup here in terms of how things are set up in increasing acidity. So as we look on that second row of the periodic table between carbon, nitrogen, oxygen, and halogens and fluorine, for example, we can see an increasing acidity from the left to the right. So if you remember from earlier in the semester, we talked about the size of those atomic radii for where those electrons are found. And as we go from left to right, the size actually decreases and we get smaller and smaller. And the reasoning, again, is because we have more protons being packed into the nucleus, and the shell where those electrons are going to kind of be in the same spot until we get those protons pulling on them, so it actually gets smaller. So the size of that shell gets tinier and tinier because the electrons are getting pulled in towards that positive charge in the nucleus as we increase the charge state. And if we think about these, now if we have a proton here that's attached, these electrons are going to get drawn towards that nucleus, and then that proton is going to be easier to be released, where the electrons are going to be closer and pulled towards that fluorine. So this release is easier for that hydrogen. Now when we're looking at the halogens going from the top to bottom, we have something that now we have these bigger shells. And it's not actually the fact that where the protons are and the electrons, but it's actually the conjugate bases that you can see over here that are actually more stable. These are more happy. This iodine as a negative charge, if we have that negative charge distributed throughout a bigger shell of electron space, it's less dense. And so the less dense, that's more happy in terms of its stability. So it's partly because of the conjugate base is more stable that we can have an increasing acidity as we go down the periodic table in terms of size. If we zoom in and just kind of again look at that second row of the periodic table, we can see carbon, nitrogen, oxygen, fluorine here attached to different hydrogens. And we can see the pKa 50, 38, 16, 3.2 from that table that I showed you that we looked at for the earlier in the lecture here. And you can see those numbers reflect that changing pKa value and the increase in acidity from left to right. We can also think of this in terms of electronegativity, and just as an example, looking at oxygen compound versus a carbon, if we have a negative charge on our oxygen, which is more electronegative, and remember we always draw the electronegativity out with using these diagonal lines to kind of demonstrate that, that electronegativity is going to be greater on the oxygen than it is on the carbon. So if we have an OH minus, this is a more stable conjugate base because that oxygen is more electronegative than the carbon. So the stability of the conjugate base is also an important part of that, determining if something is a good acid or not. And as we go from in the halogens, we'll just use this as an example, but as we go from the top to the bottom of the periodic table, we can see that those size of the atom gets bigger as we go down, for example, between fluorine and bromine, and they are going to those negative charges. That negative charge is distributed over a larger space, and that provides some stability in terms of where those electrons can be located. And so that is why as we go from the top to the bottom of the periodic table, as that charge distribution is allowed to happen, we're able to distribute that negative charge over a larger area of space. So without looking at that pKa table that we've been working on, we can actually understand which of these are going to be a stronger acid or base just based off of the periodic table and where it is on the periodic table. So I'd like you to look at these two problems and post that answer in our Blackboard space. I'm going to just do one of them. I'll do the first one for you, just kind of to walk it through in terms of looking at these two different things. So if we're looking at the difference between really the oxygen and the fluorine in terms of which is going to be a better reactant here. So O and F. So we know that F is more polar than oxygen, so this should be a stronger acid between the two. And that's just based off of where it is in the periodic table. The next question that we're looking at in terms of what is going to be a better acid or base is we're looking at sulfur versus oxygen. So we're looking at oxygen, versus sulfur. And then I'd like you to use those ideas that we were talking about on the last few slides in order to answer this question. Post your answer in our Blackboard space. We can start using these concepts of pKa and acidity and basicity to understand some of the chemistry that's happening with more complex compounds. So this is an example of a nasal decongestant of pseudoephedrine, and we have some different functional groups in here, and hopefully you can sort of understand or see where those are. So typically, just as a convention, blue atoms are nitrogen and red atoms are oxygen. So here we have an alcohol group, and then here's an amine. Which one's going to have the most acidic hydrogen? And that would be on the alcohol group. We can either go back to the periodic table and look and see where we have carbon, nitrogen, oxygen, and fluorine on the top. And if looking between an oxygen and a nitrogen, we know that the oxygen is going to be more acidic when a hydrogen is attached. So that is the hydrogen that would be most acidic in pseudoephedrine. As kind of a side note, pseudoephedrine is often used as a reactant to generate methamphetamine. And really the only difference is this alcohol that we were just showing you is replaced and reduced from a hydroxide to a hydrogen that generates that. So a lot of other changes are typically made to generate different types of nasal decongestants that have extra chemistries on them so that we can't as easily convert these things. So in terms of Sudafed PE, will actually have some other groups on this chain that will actually make this as a conversion, even if we reduce this, or it'll block that reduction because it'll have a more reactant side chain that would react first. So it would require multiple steps to get to this, which a lot of people can't do in their kitchens, for example. So that's why there's a restriction on how many of these you can buy typically in the store if you go over the counter. But some of the versions, the Sudafed PE, for example, are less regulated because of that molecular change. So other things that are interesting that can induce or create changes in the acidity of certain compounds, that table is a good starting point. But there are other things that can influence the acidity, and one of those are these inductive events. If we have an alcohol functional group shown here, so it's an ethanol group compound, and we have the alcohol here. If we change this so that we have the protons on the end are going to get replaced by fluorine, we know that fluorine is more electronegative, so we'll actually pull electrons out from that carbon. So we'll get a partially positive center here on the carbon that's next to the oxygen. And so this kind of pulls electrons away, and this helps to pull electron density away from that oxygen and away from the hydrogen. So we actually find out that this is a stronger acid because of those inductive events. You can see that when we're looking at the conjugate of that system, the conjugate base, we also see what happens, that we get this really dense negative charge. So this is kind of a heat map, and the more red it is, the more electrons and electron density is shown. When we get those charges pulled towards those fluorines, that distributes that charge better, and this becomes a better, more stable conjugate base because we're able to distribute that negative charge more throughout the whole compound. And anytime you can do that, that stabilizes the structure, and any stabilized structure is more stable. So this release of that proton doesn't result as in as strong of a condensed charge state. So let's look at this problem here. We're looking at glycolic acid, which has the formula shown there, and it's a simple member of a group of alpha hydroxy acids. and commonly used in various skincare products. We want to look at the difference between the stronger or weaker acid than acetic acid. So let's draw this out, and we're going to have this carbon. I'm going to start with the carbon backbone. So I know I have 2 carbons in a row, and C, and then I have an alcohol group here, which is shown here, and 2 H's attached to that one carbon that I can see from here. I have another carbon with 2 oxygens. Whenever I have COOH, that tells me it's not COOH. This is something that we will probably never see in this class or very frequently. This isn't typically what we're usually going to generate. So this COOH tells me it's a carboxylic acid. So that's just something that as you practice these, you'll recognize that it really never means this group. So then we have that group. So that is our compound that we're going to look at in terms of that top compound. And then we're also looking, so we want to look at acetic acid. So CH3, COOH again. So we'll have that compound again. So now we can see which one's going to be the stronger acid. And really the only difference between these two are going to be that alcohol group that is going to be replacing a hydrogen. And when we talked about that last slide, we talked about inductive events. Remember, there's going to be a partial positive, partial negative charge here, and there's going to be a pull of electrons away from this carbon. Where down here, there's no electronegativity differences between the carbon and any of its bonded elements. So we'd expect that because of those inductive events, that this would be the stronger acid. And this would allow that density, that electron density, as we generate the conjugate base, to be stabilized. So that negative charge can be distributed as we get pull from the right to the left towards the electronegative oxygen here. I want to look at another idea here if we're looking at a paradox between HBr as a stronger acid than HCl, but if we put in an oxygen, then we have HOCl versus HOBr. So what is the paradox between these two if the HOCl is a stronger acid than HOBr? And again, the paradox would be because we have the HBr, the bromine is actually larger, right? So we'd expect this to be a stronger acid because the conjugate base is more stabilized as a negative charge compound. But now when we look at the difference when we add that oxygen between those two, we have a difference in the electronegativity difference. Oxygen and chlorine are actually on that diagonal, and they have a similar electronegativity difference. Whereas the HOBr, the bromine, is less electronegative. So we'll have electrons being pulled towards that oxygen. And so that creates this disparity between, if we would lose that, we would have a more dense negative charge on that oxygen, which makes it a less stable environment as a conjugate base. So this conjugate base system is more stabilized than this one down here. I also want to talk about resonance effect on acidity. If we're looking at ethanol versus acetic acid, why is acetic acid with this carboxylic acid functional group, what makes it so much stronger? What is the difference that's really happening here? So if we look at the reaction, we're going to kind of move those electrons between here and look at what our conjugate base looks like. So we have a conjugate base system here with that carbonyl group. These electrons have the ability to jump between this carbon and oxygen and then push those electrons up towards the top. So you can see here there's actually a resonance structure. We can flop back and forth between the double bond between the carbon and the oxygen on top and the carbon and the oxygen to the right. And this provides some stability, more space for those electrons to flow in. Ethanol, when that one releases that proton, those electrons can't go anywhere. There's nowhere else to move those. They're not going to go on this adjacent carbon because then it would have too many electrons on it. It would be over its octet. But here we're able to move those around and distribute those, and this allows some stability, and that's what really provides this as a stronger acid, because the conjugate base is more stabilized. Now I'd like to also look at the difference between ethane, ethene, and acetylene. These are single, double, triple bonds, and it really has to do with their hybridization character of their orbitals. So if you remember, if we're looking at this carbon, we have 4 different orbitals, and instead of an s and 3 p orbitals, it's actually 4 hybrid sp3 orbitals. And this one, because we've hybridized all of them for that sigma bond, it's about 25% of this is s-like. But when we go here, we have to unhybridize one of those p orbitals, and we have an sp2 hybrid orbital, and one of the p orbitals is being used for that double bond. And as we go to an alkyne, then we have to unhybridize 2 of those p orbitals, and we have an sp hybrid orbital. So as we go from left to right on this chart here, we can see we go from 25 to 33 to 50% S-like, and the more S-like, the kind of rounder that shape is of the hybridization state, and the more those electrons are held in towards that carbon. So the closer the electrons are to carbon and they're less pin-like and elongated, the more acidic that is, because of where we're going to have that compound. We can also see that as we look at the conjugate base of those different acids, that change in the S-like characteristic allows us to distribute that electron, that negative charge, more along the whole entire element, versus if we have the alkane. We can see a really bright red spot here on our kind of heat map. On our heat map here we have, it's a little bit reduced, it's a little more orange than it is red, and then here it's mostly kind of orangish, and it allows us to distribute that better. And again, the less of this heat map, when we have these harder kind of negative charges, that makes it less stable. And when it's able to be distributed better, that makes it more stabilized. And when we have a more stabilized conjugate base, that allows the chemical reaction to happen more readily. So here's just a summary of those acidity factors and those things that change if we're looking at the periodic table from left to right versus up to down. We have differences in what is going to determine if something is more or less acidic. We have the inductive effects of things that are attached to adjacent carbons that help pull electrons and stabilize our conjugate base. The resonance effects are oftentimes also stabilizing conjugate bases. And then the hybridization, mostly we're talking about, in that sense, we're talking about single versus double versus triple bonds to help with increasing acidity and distributing that negative charge in our conjugate bases. So just some different things to think about, or ways to look at acids and bases. So we've spoken about Arrhenius acids and bases, Bronsted-Lowry acids and bases, and now the final kind of definition of this are going to be Lewis acids and bases. And Lewis acids and bases are not always Bronsted-Lowry acids and bases, or vice versa. So I'll talk about this. So if we're looking at a Lewis base, has the same definition as the Bronsted-Lowry. So we're looking for these lone pairs of electrons. We're looking for the lone pairs of electrons. Here or here are examples. Or we're looking for those pi bond electrons in double or triple bonds. We're looking at Lewis acids now that are Bronsted-Lowry acids. That's when we have protons to give. So if these are going to be attractive sources of protons, or those are going to accept electron pairs. But really, where we're talking about Lewis acids that are not Bronsted-Lowry acids, it could be anything that's going to accept an electron. So if we're looking at, we looked at this example a few lectures ago. We're going to have a partial positive charge, partial negative charges on the fluorines, and that is going to be an attractive source for nucleus, right? So we're going to be able to be attracted to that as a lone pair of electrons because of that partial positive on that boron. So this can actually act as a Lewis acid, and it kind of bridges the gap between some of the chemistry we see in organic chemistry And it just provides this understanding of really the difference is that we're going to be an electron acceptor, and it doesn't necessarily have to be a proton. So it expands that definition a little bit more. So as we go from all of these different explanations or descriptions of acids and bases, depending on who's coming up with them, is just talking about something a little bit different in terms of what the research and what the things that they were studying at the time involved. Here you can see that this boron has this open p orbital that's vacant, that has nothing in it. And since it's partially positive, those electrons will be attracted to it. So in a Lewis acid definition, electron acceptors have to have the ability to accept a pair of electrons. It means usually they're often positively charged or partially positive, or have opens or vacancies in electron orbitals. So remember, Lewis acids and bases Lewis bases are the same for all of them. So if we're looking at this problem where we're looking at Lewis bases, we're just looking for lone pairs of electrons or double bonds. So we have a lone pair there. Here we could draw out the Lewis structure. It's going to be all single bonds, and we can kind of do that by drawing out that Lewis structure. So we know that B would not be a Lewis base because there are no lone pairs. And H minus means that we would have something, a lone pair, so that could be a Lewis base. And then here we have pi orbitals, so we have also Lewis bases. So A, C, and D would count there. How about the Lewis acids? That means that we have to have some ability to bond or allow the donation of a lone pair. So this boron only has 3 bonds. We have an open orbital, so we could use that as a Lewis acid. See, here we have a compound. And we would be able to accept electrons here. So this could act as a Lewis acid. So F could also act as a Lewis acid. Here we have a positive charge, so we can act as a acid as well. And bromine, if we have this, if we look at how many lone pairs it would have to have a negative charge on it, it would have to have 8. There's nothing that it couldn't accept any more electrons. It's got the octet. So this one we would not consider as a Lewis acid, in addition to the fact that it has a full negative charge. So E, F, and G would be Lewis acids in this example. A lot of times when we're talking about Lewis acids and bases, we change some of the definitions. Instead of the acid and base, we talk about electrophiles and nucleophiles. And we're looking for electrophiles want electrons. So they'll typically be positively charged or partially positively charged. And these are going to be similar or analogous to the Lewis acids. Where we have the nucleophile, we're going to have these lone pairs of electrons are fully negatively charged. They want the nucleus, so they're going to be attracted to the nucleus. Nucleophiles, they're also analogous to the Lewis bases. So here are some examples of those. And then you can see that complex, the new bond that's formed with that arrow formalism showing where the electrons are going to form bonds between these two different atoms. Here, the bromine and the carbon, and the chlorine and the aluminum that are formed. Here I'd like you to show, using curved arrow formalism, how these things are going to respond to each other. What is the chemical reaction going to be? And I'll do A for you. I'd like you to do B on your own and post that in our Blackboard space. But we know that we have a base here because we have lone pairs of electrons. And we have a partial positive here if we look on the periodic table, looking at boron, between boron and fluorine, one of the more electronegative elements. We're going to have these differences in electronegativity. So this is how I would determine what's the acid and the base. And here we have the electrons are going to flow towards that partial positive, and that's likely what we're going to get. And then we have that B is attached to those 3 fluorine still, and now we have an oxygen with a CH3, CH3. We have a lone pair still, and that's going to be positively charged because we have 3 bonds, and the boron is going to be negatively charged because we have 4 bonds. And again, you can do that calculation looking at the formal charge description looking at the valence electrons versus the bonded electrons. Now for B, I would like you to do this one and then post that answer in our Blackboard space. What is that going to look like? Finally, one more practice, just using this curved arrow idea. I'd like you to try to practice this and look for what is going to be the acid, what is going to be the base, how are these things starting going to turn into what is in the products, right? So how are the reactants turning into the products? What is moving from one thing to another? And then how do you depict that using arrow formalism? So please draw this out and post this in our Blackboard space. So this is going to conclude this chapter, and then we're going to kind of more briefly go through some of the chapter 15 content that looks at the different types of organic compounds. I've kind of sprinkled this in already for these earlier chapters, so the next set in regards to chapter 15 will be a little more condensed.